Good afternoon, everybody. I hope today I can do what I'm planning for. I'm planning to do review the open circuit test and short circuit test to determine the equivalent circuit of a transformer, which is really very important topic. And you are going to have your first experiment for transformer next week. And I advise you to start on the pre-lab work because there are many questions in the pre-lab work. And if you follow the steps after the lecture, I think, I mean, you will understand well. It'll be really easy. And the second thing I'm planning today to do another example. So first, I want to explain what does it mean open circuit test and short circuit test. Last lecture we started and we talked about it, and I'm going a little bit in detail. If we have transformer and we want to find or determine the parameters of the transformer, we should perform two tests. The first test we do, it doesn't have to be in order, by the way. When I say the first test, doesn't mean, I mean, you got to do that, the first thing. You can do open circuit test or short circuit test, whatever, in any order. But let's just start open circuit test. What we'll do, we get the transformer. And we have two sides. In one side, we are going to measure the amp with a meter, and we are going to measure the power, and we are going to measure the voltage. On this side, we are going to connect the power supply. AC, of course, has frequency and has voltage, and barrier. And I start from 0. On the other side, I leave it open, so no load. So the current here, if we call this N1 and this is N2, we always will prefer to the primary 1 and the secondary 2, just to make it simple when we write the variable names. So that will be the current I2, it will be 0. So when you go to the lab and you will see in the sheet that we are connected already resistant to make it ready for the second step, all what's supposed to do, turn off all switches be on the down position to make sure nothing is connected. Or you can separate the two wires to make sure it's no load is connected. And what happened here, they don't have load, so the power supply is going to supply whatever the transformer going to consume. The transformer in this situation when there is no load, so the all power not going to the load because there is no load. So it's going to cover the core loss in the transformer. And that's why I explained last time, it gets hot. So this wattmeter is going to measure the constant loss in the transformer, whether load is connected or not. So that will, the power here, it will measure the core power loss, which we call it PC, core loss. What's core loss? I said, I mean, just when the magnetic field is alternating, intersecting with conductor, so it will produce EMF, circulating current, getting hot. So that's, I mean, power loss, the core, in the core, it's happening in the core. Sometimes you call it also iron loss, because I mean, the core made of iron. Okay, so what we'll do? Well, so we'll say in this test, in open circuit test, that's open circuit test, we'll observe the following. One side is open and the other side, you put the instrument. So one side is open circuit and instrument on other side. They prefer to open circuit will be on the high voltage side, and they like to put the instruments or measuring instrument on the low voltage side. Why? Because at no load, it is sufficient for low voltage to obtain rated flux in the core. It's just simple. Because we don't have load, so we don't need high voltage to start or reduce the magnetic flux, it's just enough. So we don't have, yes.
What does no load mean? That just means that there's no current in the.
As you see here, I2 is equal 0, you don't connect any load. Yeah, open. I2 is equal 0. So it's preferred, we'll say it's preferred that the open circuit will be on the high voltage side and the measurement will be on the low voltage side, and that's the reason. Because low voltage is enough to produce or to obtain the rate flux in the core. Well, why we do the open circuit test? To find the following: core loss, and sometimes you call it iron loss. And this loss is constant, does not depend on load, obviously. Doesn't change with load even. Core loss in the transformer. And also to find the magnitude of no load current, because the current here will be going I1 at no load, so no load current. And we are going to use it to find the magnetizing branch. What's the magnetizing branch? The equivalent circuit at no load, it can be represented by a parallel branch has resistance RC and inductor has reactance JXM. And the current in this one will be IC, and the current in this one we'll call it IM, and the magnetizing current I phi is the total current, and the current I1, and here, as you know, that's I2 dash, which is equal 0. What's I2 dash? It's the reflected current in the secondary. And since the secondary is open circuit, and as we said that I2 is equal 0, so the reflected current I2 dash is 0. So actually the all current obtained in this side I1, it's equal I phi only. So in this case, I1 is equal I phi, and we're talking about vector, and it's equal to currents IC and IM. Because I phi will be divided into 2. And they are perpendicular because one is the resistant one. Well, how can we use the measurement in the lab to find all these things? The main objective to find RC and XM. So that will help me to find the equivalent circuit. So I will do it in the lab. Well, I will have open circuit here. And I have in the lab, you are going to use a meter and voltmeter, E1 and I1, to measure the voltage and the current. And then, as you know, when you run the software, you get also the power. You can find P, Q, S in the bottom, the third one. So you get the measurement. The I1, I'm going to call it I open circuit. Why I'm saying I1? Because I'm putting everything on the side, on side 1. If you're on side 2, you get 2. So I1 is equal IOC, and the voltage you're going to measure, that's the voltage open circuit, and the power you're going to measure it's the power of open circuit. Just I'll do it like that. How can you find RC? RC, this is the only one consuming power. So we'll say that the power open circuit, it's equal the voltage square divided by RC. And if you find that on side 1, you write RC1. If you put the instrument on side 2, it will be RC2. Depends what side. So I'll leave it without anything here. So the voltage is given, the power is given, so you can find RC. So RC would be equal to the voltage open circuit divided by the power. And the second thing you'll do, you want to find XM, but to find XM, you got to have IM to divide the voltage. By the way, the voltage is here. That's V1 across. That's the, let me show you the transformer. That's the transformer, that's V1 here. And that's I2, and that's I2 dash will be equal 0, right? So RC is equal the voltage square over power. I want to find XM. So XM is equal the voltage V1 divided by M. So I would say that XM is equal to the voltage open circuit divided by IM, but I don't have IM. I have only I open circuit, which is I1. Well, you can find IC now. Why? Because you got RC and you got the voltage. So if you divided the voltage V1 by RC, you get IC. So IC is equal to the voltage divided by the resistance you just got here. So now we have IC in this branch, and you have the I total I5 is the same I1. It's measured I open circuit. So if you subtract this current from this current, you get IM. But be careful, they are not on the same line because they are perpendicular. Let me show you what does it mean. That's the voltage of open circuit, and that's the current if lagging. It's lagging almost. That's I open circuit. So if you make resolution, you will find that there are two components, one component here and one component there. The one component with the voltage in the same voltage, this is the one that consumes power. That's IC. IC in phase. Why? Because look at the branch. That's IC in RC and this voltage. And you know, in resistance, the voltage and current, they are in phase. So that's IC. However, the other one, IM, is perpendicular because it's on the reactance. And the difference will be 90 degrees. Why? Because if you divide voltage by J, let me just show you one example. If you divided voltage by JXM, give just number. If you have 100 divided by J10, what you get? Minus J10. It means 10 or negative 90. Here you go. That's so, all right. So how can you find IM? Well, you know from this graph that I open circuit is equal to the square root of IC square plus IM square. So if you want to find IM, so IM will be equal I open circuit square minus IC square Pythagorean. Then you get IM, the current in this branch. You have this current, you have all this I1 is equal I5 equal I open circuit. All this, that I call it I open circuit. So if you subtract, but not just by Pythagorean, you have the I total, I open circuit. You have IC, now you get the IM. Use it by Pythagorean. Once you get IM, and you have the voltage across the same voltage here across XM, you divide the voltage by IM, you get the value of XM. Without J, you get the value only of XM. So now XM is equal V open circuit to IM. You got IM here. You got XM. So now by this test, what you got? You got RC, which represents the core loss. You got XM, the reactance, which is responsible for the mutual flux in the core. That's what you need. You can get, and you got also the open, the no load current, which is I open circuit. You measure. That will give you idea how much current when we don't have load. As I told you last time, when you plug the adapter or transformer, you don't connect it to anything else. It gets hot. Why getting hot? Because of that. So in this test, we found the no load current. We found the core loss BC, which is equal exactly the watt meter reading BC, and we got also the magnetizing branch, which is really important to complete the equivalent circuit. So that's one test. Some maybe ask, okay, which side this one? This side one. Said, okay, what about if the question find everything on the other side? Just use the turns ratio for transforming one impedance to another. Well, I forgot it. How I do it? I will show you. If you have a transformer and call this N1 and call this N2, and let's say that you have impedance here. The impedance here is going to be called Z1 because you are on the side N1. And you want to move it there, you find the equivalent. I'm going to call it Z1 dash. So Z1 dash is equal Z1. And since you are going here, that's N2. So I say times N2 over N1 squared. And then you can see where is your A. Is your A in one? Always, I mean A, always A in one over in two. But I'm saying if you want to use A. But if you don't want to use A, you can just do it like that. What about if you have impedance on the other side? That's N1, that's N2, so that one we call Z2. And I want to refer it here. I find the equivalent. Okay, so let's say, okay, I'm going to N1. So I will call this not Z2, Z2 dash, the equivalent will be equal Z2 times N1 over N2 squared. It's just simple. Don't worry about A if it does bother you. So now, I mean, we got the open loop test, we got the magnetizing, called magnetizing branch RC plus JXM, and I can refer it inside. All right. Now we'll go for the second test. The second test is called short circuit test. How will we perform short circuit test? Well, we'll get the transformer again. That's one side where you put the instrument, and the other side you are going to make short circuit. So you are going to replace the load by a wire by R equals 0 or Z equals 0. Short circuit. Of course, there is a big current going there. And you are going to put your measuring instrument. Here you go, the ammeter, the voltmeter, the wattmeter. And of course, you're going to connect the voltage, and that's variable. And always start from 0. Always make sure 0. Even in the lab, you are making short circuit test, or you are going to bear the transformer will be there now. So start from 0. Make sure it's 0. You put it in 0 and make the short circuit and start gradually to increase the voltage. Let's call this N1 and this call N2. First, very important, voltage is increasing gradually. Start from 0. Always start from 0. From 0 voltage. And you start to increase the voltage UI on the ammeter in the lab. And try to get closer to the rated value of the current on the side. And you stop the voltage. Usually, practically, if you have the rated voltage known for the transformer on the side, it's usually between 2 to 12% of the rated voltage. Like if you have 100 volt, maybe we just reach to 12 volt to reach the rated value of the amps on the side. So you start from 0, increase it till the current on the side, that's I1, reach or get closer to I1 rated value. They prefer to have the short circuit on the low voltage side, and they put the instrument on the high voltage side. Why? What does mean high voltage side? High voltage side, it's just as the name says, high voltage. And as you know, in transformer, the voltage get higher, the current get low. The voltage get lower, current get higher. Why? Because power is constant, and power equal V times I. So if the power is constant, V get higher, I get lower. So they prefer to put the instrument on the high voltage side. So the ampere will be reasonable. Why they are doing the test? When they measure, what this watt meter is going to measure is going to measure the copper loss in the transformer. What does it mean, copper loss? Yeah, it means everything lost in the resistance of the transformer winding itself. And you can use this test to find, with, as you said, copper loss. All right. But you get the copper loss at full load also. Well, what does it mean? Because when you are increasing the voltage on this side, your eye on the ammeter, and you are adjusting till you get the rated value of I1. So you are finding the power loss near the full load, which is important to know. And also, you can calculate the short circuit current, so you can protect your transformer, because you want to know if there is fault, and always happen fault. If there is fault and you want to put circuit breaker in your system, fuse. So what is the rated value of the fuse? Are you going to put 5 amp, 10 amp? You just don't put any fuse. No, you got to protect it right. So usually the protection depends on the short circuit value. So you be able to find the short circuit current, and you are going to find the equivalent impedance of all transformer winding, R equivalent and X equivalent. You will get both the equivalent impedance of the transformer, of the winding transformer. Of course, will be referred on the side where you do the test. All right. Remember, what is R equivalent and X equivalent? Each winding has resistance and leakage reactance, as we explained last lecture. Like if you have a winding here, and let's say that's N1 and that's N2. This one has equivalent impedance. You can say R1 and JX1. Its own winding has R1 and JX1. And the other side, N2, it has its own winding, it has its own resistance and inductance. So you will have R2 and JX2. And as you know, you cannot work in two separate circuits. In circuits, you have only one circuit. So what you'll do, you might take this and refer it there, or you might take this impedance and refer it on the other side, whatever the best scenario or whatever the problem is. So let's say that you want to move R2 and GX2 to the other side. So in the end, you will have R1, GX1, you were there. And then you got the reflected, called reflected impedance. So we'll have R2 dash and JX2 dash. That will be your transformer, ignoring the magnetizing branch that I talk about in open circuit test. I'm talking about short circuit test now. So you add R1 and R2 dash, and you just call it R equivalent 1. Because you find the equivalent resistance of the whole transformer for both winding, but referred on the side 1. And you add the X's together, so you have JX equivalent 1. So simply that's the equivalent of your transformer, ignoring the magnetizing branch, where R equivalent 1 is equal R1 plus R2 dash, and X equivalent 1 is equal X1 plus X2 dash. So that will be the equivalent impedance of the transformer referred to side 1. You want to do the other side, you can do the same thing. You will have R equivalent 2 and X equivalent 2. Let's take one numerical example. How to find all the things by real test, like exactly what you're going to do. You are going to do in the lab exactly the same thing we're doing now. That's why it's very important to start working in your pre-lab, before you go to the lab, don't say I'm going to do it 1 hour before. No, I'm telling you, if you make it even 2 hours before, you'll not be able to submit it on time. You have to do it at least 1 day before the deadline. Like if you lab Tuesday, don't do it 1 day, do it Sunday. If you want to take vacation someday, make it Saturday. You want to take Sunday vacation, make it today. That's the plan. Don't say, no, I'm going to do it in 1 hour and Monday. No. You will come to the university, you have lectures, you don't have time. So let's take now, I will go back to the example I just wrote. That's test. Transformer. Let me just cut this one ticket. Yeah. All right. So that's the data of the transformer. And it's very important to know that's the rating value, 10 kilovolt amp, and that's the voltage on this side, this side. Of course, there's low volt side, high volt side. But I just, you know, I like to be simple. I will just call this side 1, this side 2. All right. And the frequency. Before you do anything for the test is given to you. The results, the data is given open circuit test. That's the result, the voltage, the current, the power, the same thing, but you don't know which side. It'd be nice if the problem told you that these measurements were on side 1 or side 2, but it didn't say. Is it fair? Yes, it's fair. So what will help you? First, find the rated value of the amps in each side. How we get that? That's the rated value. First of all, you can find the turns ratio. Turns ratio is equal N1 by N2, and already that's 1, that's 2. So an N1 will be 480 voltage by 120, which is equal to 4. Is it practical? No, it will not be exactly 4. This is a voltage will be less, you know, the bit, but be 3.9. That's okay. So that's the turns ratio. That's the first thing. And I'm going now to find I rated value on side 1, and also I'm going to find the rated value on side 2. The rated value on side 1, I'm going to divide, that's S, by the way. That's the apparent power, volt amp. So I will divide S. Somebody will ask, is S1 or S2? Doesn't matter, because both are equal on both sides. So I write S. And then I divide it by the voltage rated 1. Rate R, okay. R is not resistant. Okay. How can I get out of this one? Do you understand R is not resistant? I rate it. Okay. So I'll just R rated means rated value, not resistant. And VR1, the same thing. So S divided by VR1 equal, the apparent power is equal 10,000 volts, and divided by VR1, VR1 is equal 480. That's equal to calculate here or not? Okay, that will be equal to 2083. You guys, if you have calculators, you can check by me. That's IR2. You'll divide the apparent power by VR rated value on the second side. That's 10,000 amp, V volt amp, and the voltage rated on the side 2, 120. So obviously we are going to have a higher current. That will be 83.33 amp. So that's the first step you do. And now we're going through the test now. So the first thing you do, you have the rated value of transformer, get your turn ratio, get the rated value for the current on each side. What does it mean rated current? It means that it's not preferred, it's advised that when we use any load, do not exceed the rated value to keep the transformer lifetime and expand. So now we'll go for open circuit test, the first one, open circuit test. The information is given here. 120 voltage, 2.5 amp, and 6 watt. When you look for open circuit test, look for the voltage. Because always, as you said, in open circuit test, they use the rated voltage. because you don't worry about the amp, it's open. So when you look at the voltage, what you have? 120 volts. Then you check 120 volts, where the 120 voltage? On side 2. So what does it mean? You open circuit side 1 and you put the measuring instrument on side 2. And they apply the voltage from side 2. That's the meaning of it. So it means that that's a transformer. And that's side 1 and that's side 2. So you put everything here. So the voltage was here. The 120 voltage. And then they start to take the measurement. The amp and power and everything. So now, okay, when you get the equivalent magnetizing branch, which is RC and XM, will be at 2. And if you do it to refer it to 1, it's easy. We'll use the turns ratio. First, how can you find? Okay. First, I will just to make it simple, I will say that the equivalent the equivalent magnetizing branch, you have RC and you have X. And that's the current, that's I open circuit. Obviously, that's from I2. I don't care, it's I2 or I1. That's the open circuit. And that's the open circuit. And the power is given also. The data given in this table, 120 voltage, 2.5. So that's 120 voltage. And by the way, all magnitude. And open circuit was 2.5 amp. And if you have watt meter to measure, so we got 60 watts. So I'll say, okay, the cool loss, the cool loss, it's equal to 60 watt, which is equal to volt open C square over RC. That's RC. So RC will be equal to the voltage square divided by the power measurement. The voltage square is equal to 120 square divided by the power, which is equal to 60. So you get RC equal to 240. But to be, cautious, since you know the old measuring instrument on side 2, so write this RC2 to know where it is. So I'm doing that just to make it clear. That's RC2. Now, once you get that, you put the value, 240 ohm. Then the second step, find IC. How you find IC? Just divide the voltage by the RC. So IC2, because on side 2, is equal to the voltage divided by RC. The voltage is equal 120 divided by 240. That will give you 0.5 amp. Ohm.
Wait, so the amps are ohms?
Ohm. The resistance. Oh, I'm sorry. Amp. That's 0.5 amp. That's good. Yeah, that's that. Yes. So once you find IC2, the second step, find IM2 directly. How you find IM2? You will say IM2 is equal to the total current I open circuit minus IC2 square. The total current here 2.5 square minus IC2, we just got it 0.5 square amp. And then you calculate IM2, which is equal to 2.45 amp. You got the IM2. Once you get IM2, you can get directly XM by dividing the voltage by I. These steps just systematic. So XM, and you write 2 because inside 2 is equal the voltage divided by the current. The voltage is equal 120 and the current is equal 2.45. That will give you 49 ohm. So you got the XM 49 ohm. You just put it there. Now that's all what you need. So let's say that in the problem they ask you to find the equivalent circuit on side 1. From now, do it. How will you do that? You are in 2, you want to go to 1. You are in 2, you go to 1, so you want to find actually RC2 dash, or let's call it RC1. You know what I mean, RC1, and you want to find XN1 instead of 2. So we'll say this is equal RC2, and you're going to 1, so N1 over N2 squared. And XM1 will be XM2 times N1 over N2 squared. And you have N1 and N2, and you get them, you will get 3,840 ohm, and X is equal 783.8 ohm. You got the equivalent branch on site, yes.
Why did you multiply RC2 by N1 over N2 squared by squared?
Well, because I mean, when you find the reflected impedance I explained here, when you want to find the equivalent impedance from one side to another, you multiply it by 10 squared. And let me tell you why. Let's say that you have R2 on this side, and you want to get it there, and you want to call it R1. You want to go there and we call it R1. And you know that's N1 and that's N2. The main principle for moving anything from one side to another, not only electric system or mechanical system, chemical system, you should preserve the power and energy, be the same. So what is the power here for this one? That will be I2 square R2. And if you move it to be R1, so it will be R1 times I1 squared. They should be equal. So what is the equivalent? R1. R1 will be equal to R2, I2 over I1 squared. What is I2 over I1? It's equal N1 over N2. Yeah. So now we know how to find the magnetizing branch in either side. Yes.
For the value XM2, is this supposed to be V over circuit divided by IM2 instead of RC2 XM2?
Oh yeah. You're right. Yes. That's right. We divided by the current IM2. Yes, absolutely right. And even I wrote the value. Okay. All right. Thank you. So we are done with that. Do you have any questions? Go on circuit test. So let's see the short circuit test. In the short circuit test, we explain how to do it just to get the data, see where they did it. So the short circuit test, you don't look for the voltage. Not like open circuit. Why? Because always we start from 0 and increase it gradually. We never go to the rated voltage. We try to get close to the rated amp. So to know where is the measuring instrument, you look for the amps in short circuit test. So when you look for the short circuit test, because I mean, you look at the voltage 26 volts, you don't know where it is. Yeah. You look for now for the amp, it's 20.8 something, like around 2021. Now you go for the values of the amps, the rated values for the amps that you did before. You got IR1 is equal 20.83, you got IR2 equal 83.3. So where the current of the short circuit was measured on side 1, side 2? Side 1, that's right. What does it mean? The short circuit side 2, and they put the measuring instrument side 1. We go now for side 1. That's 480 and 120 voltage side 2. And we agree that it's closer to IR1. So when you sketch the circuit, I1 and I2, all right. So now you will say this is your side 1, N1. And that's your side N2. In open circuit, they had the instrument there. No, now I mean the short circuit is just it will be on the other side here. And all measuring instrument will be there. Well, I will just write what the voltage that they measured. They found that the voltage increased up to 26 voltage. And the amp that they measured, it was 20.83, and the watt, the power was 200 watt. So that's the only measurement they got. So what in the end you will get? They're supposed to get that. It's supposed to get like equivalent resistance and equivalent. You get R equivalent 1 because they are inside 1, and you get X equivalent 1 because they are inside 1. They should get this one.
Are we taking our measurements from earlier, like with the short circuit test?
With the short circuit, that's what short circuit test. Yeah.
It's supposed to be 220, I think.
220. Really? Let me see. 200 watt. Yeah, that's okay. Okay. So, what does it mean? These measurements. First of all, the watt meter reads only consumed power watt, which is related to R only. All right. And you know that the current I short circuit, it was 20.83 amp. So the power short circuit you measure is the copper loss, which will be equal I short circuit squared times R equivalent 1. You got the power, you got the current, you get R equivalent. That's the first step. So R equivalent 1 will be equal the measurement of the power divided by I short circuit square. So the power is equal to 200, and the short circuit current is equal to 20.83, and make it square. You get the R equivalent. Okay, let me just. Do you guys have calculator or 200 over 20.83? Oh, thank you. That would be fast. 0.
0.461.
Like that? Okay. So that will be R equivalent. And now I'm going, and because it's measuring everything. What does mean R equivalent 1? It means R1 plus R2 dash. Right. Now I want to find X. I find X. Well, if you know the voltage and you know the current, what happened when you divide the voltage by current? Impedance, magnitude. All right, good. So I'll say Z equivalent magnitude is equal. That's 1, of course. The voltage short circuit voltage divided by I short circuit. The voltage was equal to 26 divided by 20.83, and then you get the equivalent. All right. Remember, the impedance triangle that will help you. You have the resistance is equal 0.461 ohm, and you got the impedance 1.5 ohm, and you need to find X equivalent 1. Piece of cake. So X equivalent 1 is equal to the square root of Z square 1.25 square minus 0.461 square, and you'll get the X equivalent. Once you get X equivalent 1, you got the equivalent impedance. And now, if you want to have the equivalent circuit of the transformer on side 1, so you got to do that. You will have Z equivalent 1, and you got your branch here, the magnetizing branch that we already did. That's RC1 and XM1, and that's the side is not VT now, it's V2 dash, was everything referred to, and here you have V1. If you found X equivalent, please give me the 1.16. Thank you. So now we have Z equivalent 1. I can write it now is equal to, let me just write that number. We got 1.16. So Z equivalent 1 is equal to 0.46 plus J 1.16. That's the equivalent. And RC1 we did before, RC1 3840. So 3040 ohm, and XM1 we got it 784 and J. That's it. That's it. In the lab, you have to do that. You find the equivalent circuit, and then you are going to connect a load. What happens if you connect load and you want to find the current and the voltage? Okay, let's assume that sometimes they will tell you the transformer has 75% of the full load. What does it mean? Sometimes we don't give you resistance. Most of the time, when the engineering speak, they don't say, for example, I'm going to put load 100 ohm and reactance equal to 50 ohm. We don't say that. Engineering speak like, I mean, when you have transformer, you have load. If you know the load, you give them the power and the power factor. That's one thing. So okay, what's the load that you're using transformer? Well, 300 watt, 0.87 lagging power factor. That's the language you speak. All right. We translate maybe to ohms, I think, so we can create. Yeah. Well, let's say that it was loaded like by 70. The load is equal to 75% of the rated value or the full load, and with power factor 0.866 lagging. That's the load. So in this case, you want to calculate the current here. They are using the normal voltage. When they say something like that, 75% full load, power factor, then you will ask what's the voltage. When they say that, means that they are using the normal voltage. What was the voltage? Let's go back again. We are on side one. On side one, that's 480 volt, and the secondary will be 120. So it means in the secondary is 120, but you only make the turns ratio, it will be 480. So because I'm referring everything to the side, so that will be equal to 480 voltage. What about the amp? The amp is it's telling you 75%. 75%. So how can you find the current? The current here, by the way, is I2 dash. I2 dash. What's I2 dash? Well, you know I2 over I1 is equal N1 over N2. I2 dash, that's what's replacing I1. That's I2 dash. So I2 dash is equal to N2 over N1 times I2. What's I2? I2 is 75% of the full load. So I2 in the secondary, he said 75%. So it'll be 0.75 times what? Times the rated value on the second on side 2. Did we calculate? Yes, we did. We did. That was the first step. Always we do that. IR2 is equal 83.3. 83.3. So you'll say 0.75 times 83.3. And then you get 60. 62.5. Thank you. So that will be the current on the secondary side. But now I want to find and have everything on side one. So I'll say, okay, I2 dash will be equal I2, which is 62.5, we said times N2 over N1. N2 over N1. Oh my, I forgot quickly. N2 over A1. I don't mistake. 120 over 480. 120 or 480. Quarterly. All right.
15.6.
15?
15.6.
Okay. 15.6. And so that's current here. So you just write in the 15.6. You know the equivalent. You multiply this current by the equivalent, you get the voltage drop, right? You get the voltage drop across the equivalent. So what's V1? V1 is equal V2 dash plus the equivalent 1 times I2 dash, the drop. It will get the voltage here. Something, but you have something in the middle. It's parallel. Because the voltage here, it's equal here, it's equal here. From this point to that, it doesn't affect the voltage, right? So I'll say, now we find V1. V1 is equal to V2 dash plus Z equivalent 1 times I2 dash. V2 dash, we said it's equal to 480 plus Z equivalent. Z equivalent is equal to 0.46 plus J 1.16 times I2 dash. Now there's something you have to pay attention. You think you got I2 dash right, you got only the magnitude. The current has magnitude and angle. Oh my gosh, yeah. We're working the AC. Only the magnitude is equal to 15.6. Then you ask how I can get the angle. Simple, from the power factor. The power factor is 0.866 for lagging. What does it mean? It means if you have the voltage, it was V2 like that and I2 like that, and this is theta. Theta is equal cosine minus 1 the power factor. And cosine minus 1, 0.866, which is equal 30 degrees. And lagging, so I2 vector will be I2 magnitude and the angle minus 30. Because always we choose V2 and angle 0 reference. Because it doesn't matter, it's just relative. So now I can say that I2 dash is equal I2, the magnitude got 15.6. And the angle is equal negative 30. And now you can do your equation. So V1 will be equal V2 dash 480 plus the drop 0.4 plus J. We're done, huh? Just I'll show you how you complete 1.16, and that's the M 15.6 in angle negative 30. Once you do that, you got the V1. And you can, that's that you asked for. You want to find the voltage required to supply this load. So that would be how you solve. You will find that how you do the regulation and the efficiency in the sheet of the lab. It's just formula I will substitute, but that was very important how to do the calculation. I hope that you got it because it's really, really important.